In this lecture, we take a look at Lewis structures. Lewis structures are like 2D representations of molecular structure. So in this lecture, we try to take a look on how to derive a Lewis structure given a molecular formula. So if you're given a molecular formula, the first thing you have to do is you have to identify the atom with the least electronegativity, and the atom with the least electronegativity, this is what you assign as the center of your Lewis structure. Then the other atoms with higher electronegativities, these atoms you assign at the periphery or at the surroundings of your central atom. And once you are able to identify the central atom and its peripheral atoms, you would have a atomic framework or an atomic network. Then once you have this framework, the next thing you have to do is you calculate the total number of valence electrons that you have for the molecule. So for you have to add each valence electrons of all the atoms in your molecule. How do you get the valence electrons? Usually you can use the A group numbers, which can be found in your periodic table. So for instance, for the group 7 elements, these are your halogens like your fluorine, your chlorine, your bromine, your iodine. They would have an A group of group 7, and so each of those elements in group 7 would have 7 valence electrons each. Then once you are able to get all of the valence electrons for all of the atoms, you sum them together to obtain the total number of valence electrons for all of the atoms in your molecular formula. Then the next thing you do is you connect each of the peripheral atoms to your central atom through bonds or through lines. Then you have to take note that for each line that you add, it corresponds to 2 electrons. So for each bond, that corresponds to 2 electrons. Now remember that you have the total number of valence electrons which you computed previously. So for each bond that you put connecting a peripheral atom to the central atom, you subtract 2 electrons from the total number of valence electrons. And then when you continue on doing this, subtracting 2 electrons for each bond from the total number of valence electrons, what you end up is the remaining valence electrons, which are unaccounted for. So these remaining valence electrons, you distribute them to the peripheral atoms or even to the central atom, taking note that there is a tendency for atoms or elements to take on the form of the octet fulfillment, meaning that each atom in your molecule would have a tendency to have 8 electrons around it. So later on we'll see some examples. Exceptions to this are your hydrogen. Hydrogen just tends to have just wants to have 2 electrons around it. But for a majority of the elements that we'll be looking into, they tend to want to fulfill the octet rule. And once you are able to account for all the valence electrons, then you would have your Lewis structure. Now let's take a look for this molecule over here, nitrogen trifluoride. Now your nitrogen would have the least electronegativity because your fluorine has the highest electronegativity. Usually as you go from the left bottom to the top right of your periodic table, the higher the electronegativity becomes. So for nitrogen trifluoride, the atom with the least electronegativity would be your nitrogen. And your nitrogen, this is what you would put in the center of your molecule, as shown over here. Now for the remaining atoms, in this case your fluorine, you just distribute them into the peripheral. And then you connect them together. So for each peripheral atom, you connect it to the central atom. And then the next thing you do is you account for all the valence electrons. So your nitrogen is a group 5 element. So being a group 5 element, it would have 5 valence electrons. Now your fluorine, as mentioned previously, has 7 electrons, valence electrons, because your fluorine is a group 7 element. And since you have 3 fluorine atoms, then 7 times 3 will give you 21 valence electrons for the 3 fluorine atoms. And if you add that to the 5 valence electrons of nitrogen, that would give you 26 valence electrons all in all. Now we've added 3 bonds, and each bond corresponds to 2 electrons. So 2 times 3 will give you 6. Then 26 minus the 6 electrons due to the bonds would give you 20 electrons left that are unaccounted for. So these remaining 20 electrons, you have to distribute them as lone pairs to the peripheral atoms or to the central atom. So we try to distribute them, taking note that each atom would have a tendency to form an octet. So for instance, for fluorine, we place 3 lone pairs over here, 1 lone pair here, 1 lone pair here, and 1 lone pair here. And then we do the same for the other fluorine atoms. Now if we do this, you'll notice that your fluorine would now have 8 electrons shared to it. So you have 1, 2, 3, 4, 5, 6, 7, 8. So in this case, your fluorine now has a octet, and it fulfills the octet rule. The same goes for the other fluorine atoms. Now for your nitrogen, it already has 6 electrons shared to it because it has 3 bonds. And if you add a lone pair to it, then it would have 1, 2 due to the lone pair, and then you have, for each bond you have 2 electrons there, and you have 3 bonds. So 2 times 3 would give you 6 plus the 2 from the lone pair. So your nitrogen over here would have 8 electrons shared to it, and it would fulfill the octet rule as well. So in this case, all atoms, the peripheral atoms as well as the central atom, have fulfilled the octet rule, and we've accounted for all the 20 remaining electrons that that are not included as bonds in your molecule. Now let's take a look at this example here. CCl2F2, that's your molecular formula, and you have to derive the Lewis structure for this molecule. So first, you try to identify the atom which has the least electronegativity. In this case, that would be your carbon. And then the next thing you do is you place your carbon in the middle, and the other peripheral atoms, you put them at the surrounding your central atom. And then you connect them through bonds. So for each peripheral atom, you connect it to the central atom through a bond. And then the next thing you do is you account for all the valence electrons. So in this case, you have 4 valence electrons from your carbon, and chlorine has 7 valence electrons, and your fluorine has 7 valence electrons as well. Since you have 2 chlorine atoms and 2 fluorine atoms, that would give you 4 atoms with 7 valence electrons each. And so 7 times 4 will give you 28, and you add that to the 4 from the carbon, that would give you 32 valence electrons all in all for this molecule. Now remember that we've placed 4 bonds already, and each bond has 2 electrons in it. So 4 times 2 will give you 8, and then 32 minus 8 will give you 24. So that leaves us with 24 more electrons to account for. And these 24 electrons, we can distribute them one by one, or rather by pairs, as lone pairs to each of the atoms that are present. So we can start with the peripheral atoms. For chlorine, for instance, we can add 3 lone pairs, and by doing so, your chlorine would fulfill the octet rule, because it has 2 electrons from this bond shared with carbon, and it has 3 lone pairs, where each lone pair has 2 electrons. So 2 times 3 will give you 6, plus the 2 electrons from the bond. So this chlorine over here would have 8 electrons shared to it, and it will be following the octet rule. The same goes with your fluorine, and for the chlorine and the fluorine down here as well. Now for your carbon, it does not need any lone pairs anymore because it already follows the octet rule. It has 4 bonds, and each bond corresponds to 2 electrons. So 2 times 4 will give you 8. There are 8 electrons around your carbon, and so it already follows the octet rule. So what we did here over here was we added 3 lone pairs for each peripheral atom, and 3 times 3 times 4, because you have 4 peripheral atoms, will give you 12, and each lone pair has 2, so 12 times 2 will give you 24 valence electrons, and the 24 valence electrons would correspond to the remaining electrons that remain after you subtract the total number of electrons from due to the bonds from the total number of electrons. So we have 32 valence electrons. 8 of those will come from the bonds, and the 24 remaining electrons will be distributed as lone pairs.